Every atom of gold on Earth was forged in the collision of dead stars. Every breath of oxygen you take was manufactured in the core of a sun that exploded before ours existed. The iron circulating in your blood right now required a star to die in order to exist. You think you know what things are made of, but the real question is where those ingredients came from, because the universe did not start with a periodic table. It started with nothing. No atoms, no elements, not even protons, just energy. A blinding and featureless ocean of energy with no structure and no plan. 13.8 billion years of gravity, nuclear physics, and stellar violence were required to assemble the 92 naturally occurring elements that make up everything you have ever touched, tasted, or loved. That is the story I want to tell you. And you are a character in it, whether you know it or not. Most people, if you press them on it, will tell you that atoms were always around, that they're just part of the universe the way air or space is. And I understand why it feels that way. You look at the world and it seems permanent, like iron has always existed, like gold has been here forever, like carbon stretches back to the beginning of time. But that is wrong, and I need you to sit with what I am about to say. There was a period in the history of the universe when no atoms existed at all, not a single one. No hydrogen, no helium, certainly no carbon or oxygen or iron or gold. Everything burned so hot and carried so much energy that atoms simply could not hold together. Matter, as you know, it had not yet become a feature of the cosmos. Every element on the periodic table had to be invented, manufactured, and forged. And the universe had to learn how to do it in stages across billions of years using gravity, nuclear physics, and the explosive deaths of stars. That chart you memorized in chemistry class and forgot about is not just a poster on a wall. It is the autobiography of the cosmos, written in the language of nuclear reactions. And each entry earned its place through a specific astrophysical process, some gentle, some catastrophically violent. Once you understand how each element got there, you will never look at the world the same way again. Understanding this requires going back to the actual beginning. 13.8 billion years ago, the universe emerged from a state of unimaginable density and temperature. We call it the Big Bang, but I've never loved that name because it was not an explosion in space. It was an expansion of space itself, with everything that is, was, and ever will be compressed into a volume smaller than an atom, and then it expanded rapidly within the first fraction of a second, a tiny fraction, like 10 to the minus 36 seconds. The universe inflated exponentially. This is cosmic inflation, a concept developed by physicist Alan Guth in the early 1980s. And it explains why the universe appears so uniform on the largest scales. Space itself stretched faster than the speed of light, which is allowed because it is not objects moving through space, but the fabric of space expanding. Nothing in Einstein's equations prevents that. We know this actually happened because the Big Bang left a fingerprint. In 1965, two radio astronomers at Bell Labs named Arno Penzias and Robert Wilson accidentally detected a faint microwave hum coming from every direction in the sky, and they could not get rid of it. They even cleaned pigeon droppings off their antenna, thinking that was the problem, but it was not. What they had found was the cosmic microwave background, the afterglow of the Big Bang itself, cooled over 13 billion years from a white-hot plasma to a faint whisper at just 2.7 degrees above absolute zero. It is the oldest light in the universe, and it confirmed that the cosmos really did begin in the way I just described. During those earliest moments, the temperature sat at trillions of degrees. At that energy level, protons and neutrons cannot even form. You have a quark-gluon plasma, the fundamental building blocks of nuclear matter, slamming into each other at relativistic speeds, with no structure and no order, just raw, high-energy chaos. But here's the beautiful thing about the universe: it cools. As space expands, the energy density drops, and as things cool down, structure becomes possible. Think of it like water, because steam is chaotic with molecules bouncing everywhere and no pattern, but cool it down and molecules start to organize. And cool it further and you get ice with crystals, patterns, and structure. The universe did the same thing on a cosmic scale. And every time the temperature dropped past a critical threshold, something new became possible that could not have existed a moment before. The universe was cooling its way into complexity. By about 1 microsecond after the Big Bang, the universe had cooled enough for quarks to bind together into protons and neutrons, which marks the first real construction project in cosmic history. 3 quarks stick together, held by the strong nuclear force, the most powerful force in the known universe. And depending on the combination, you get either a proton or a neutron. A proton consists of 2 up quarks and a down quark, while a neutron consists of 2 down quarks and an up quark. A simple recipe with enormous consequences. A lone proton is a hydrogen nucleus, and hydrogen is the first entry on the periodic table, which means the universe assembled its first element before it was even a minute old. Between about 10 seconds and 20 minutes after the Big Bang, and that window matters enormously, the universe reached the right temperature and density for nuclear fusion to occur. Protons and neutrons started crashing into each other with enough energy to stick, but not so much energy that they would immediately blow apart. This process is called Big Bang nucleosynthesis, and it represents the universe's first attempt at chemistry. Almost all of it turned out to be hydrogen and helium, roughly 75% hydrogen by mass and about 25% helium, with tiny and almost negligible amounts of lithium and deuterium. Nothing else came out of it. And let that sink in, because the most energetic event in the history of the cosmos produced a universe made almost entirely of 2 elements, just 2 out of 92. If you judge the Big Bang purely by its element building record, it was a spectacular underachiever, the most powerful event in cosmic history, and it could not even figure out carbon. We know this ratio is correct because we can measure it. In 1925, a young astronomer named Cecilia Payne demonstrated in her doctoral thesis that stars are composed primarily of hydrogen and helium, and her thesis committee initially dismissed the finding because it seemed too radical, contradicting the prevailing assumption that stars shared roughly the same composition as Earth. She turned out to be right, and they turned out to be wrong, and her discovery became one of the foundation stones of modern astrophysics. We also confirm these primordial ratios by analyzing the light of the most ancient, chemically pristine gas clouds in the universe, and they match the predictions of Big Bang nucleosynthesis with striking precision. Nucleosynthesis stopped at helium because the universe was expanding and cooling too fast. Fusing heavier elements requires sustained high temperatures and densities, and the Big Bang could not maintain those conditions long enough. After 20 minutes, the window slammed shut, and the cosmos went quiet. For the next several hundred million years, the universe sat in darkness, with no stars and no galaxies. Just vast clouds of hydrogen and helium gas, drifting through an expanding void, a period we call the Cosmic Dark Ages. Here is something most people do not realize. The James Webb Space Telescope functions as a time machine pointed at the end of this darkness, with its infrared instruments designed to capture light from the very first objects that ended the Dark Ages, and early results suggest that stars and galaxies may have formed even sooner than our models predicted. Right now, in real time, we are watching the universe wake up for the first time. Back to the story, because gravity is patient, unbelievably patient. Those primordial clouds of gas were not perfectly uniform, and they carried tiny density fluctuations, quantum fluctuations, from the earliest moments of the Big Bang, now stretched to cosmic scales. By inflation, regions that were slightly denser than average had slightly more gravitational pull, so they attracted more gas, which made them denser still, which increased their pull further in a runaway process. Over hundreds of millions of years, Gravity gathered those clouds into clumps dense enough and hot enough at their centers to ignite nuclear fusion, and that is when the first stars were born. These first-generation stars, known as population 3 stars, were monsters. Without heavier elements to help gas clouds cool and fragment into smaller pieces, these early stars formed at enormous sizes, with some reaching hundreds of times the mass of our Sunday. We have never directly observed one because they lived fast and died young, long before the cosmos looked anything like it does today. But in their cores, at temperatures of tens of millions of degrees, they began to do what the Big Bang could not, which was fuse hydrogen into helium in a sustained and controlled process. This reaction is the proton-proton chain, first worked out by physicist Hans Bethe in the late 1930s. And it is the engine that powers most stars, including our own Sunday. 4 hydrogen nuclei fuse to produce 1 helium nucleus. And in the process, a tiny bit of mass converts to energy through Einstein's most famous equation, E equals mc squared. That tiny bit of mass, multiplied by the speed of light squared, produces an enormous amount of energy. And that is what sunshine is. That is what starlight is. The mass difference between 4 hydrogen atoms and 1 helium atom radiated outward as photons and neutrinos. Massive stars also run a faster pathway called the CNO cycle, the carbon-nitrogen-oxygen cycle, which uses carbon as a catalyst to fuse hydrogen even more aggressively. Same input, same output, but a different mechanism, because nature found 2 ways to solve the same problem. But fusing hydrogen to helium is just the beginning, just chapter 1. Once a star accumulates enough helium in its core, and that core contracts under its own weight and heats up further, helium itself can begin to fuse. This is where the story gets truly astonishing, because the next element the universe needs to produce is carbon. And making carbon turns out to be spectacularly hard. Consider what the process demands. You need to take 3 helium nuclei, 3 separate alpha particles, each with 2 protons and 2 neutrons, and fuse them into carbon, 1, 2. But the chance of 3 helium nuclei all colliding at precisely the same instant is vanishingly small. Nature found a workaround where 2 helium nuclei first fuse to form beryllium-8. But beryllium-8 is spectacularly unstable and falls apart in about 10 to the minus 16 seconds, which is a 10 millionth of a billionth of a second. Before you can even conceive of it existing, it is gone. But here is where the universe pulled off something extraordinary. In that unimaginably brief instant, before the beryllium disintegrates, a 3rd helium nucleus can collide with it to form carbon, 1, 2. But this only works, and this is the part that matters, because carbon, 1, 2, happens to have an excited energy state, a resonance, at precisely the right energy level to make this reaction efficient. Fred Hoyle predicted this resonance in 1953 before it was experimentally confirmed, reasoning that since carbon clearly exists in abundance in the universe, a nuclear resonance must exist to make its production favorable. Think about the audacity of that reasoning. He looked at the cosmos and said that this element is here, so the nuclear physics must allow it, using the existence of life itself as evidence for a prediction about the interior of atomic nuclei. He turned out to be right. What we now call the Hoyle state was subsequently discovered in the lab, exactly where he predicted it would be. We call the overall reaction the triple alpha process, and without that specific resonance in the carbon, 1,2 nucleus, none of us would be here. No carbon chemistry, no organic molecules, no DNA. Hoyle's insight became part of a much larger breakthrough. A landmark paper published in 1957 by Margaret Burbidge, Jeffrey Burbidge, William Fowler, and Hoyle, known simply as B²FH, laid out for the first time a complete theory of how stars manufacture the elements. Think of it as the Rosetta Stone of stellar nucleosynthesis. And Fowler won the Nobel Prize for this work. Their paper explained not just the triple alpha process, but the entire chain of fusion reactions that build the periodic table inside stars. And everything I'm about to describe comes from the framework those four scientists established. Your existence depends on a specific energy level in the nucleus of a carbon atom, set by the fundamental constants of nature. If the strong nuclear force were even slightly different, just a few percent either way, that resonance would not exist, carbon would not be produced in stellar interiors, and the universe would be a very different and much more barren place. Once stars figured out carbon, the floodgates opened. Carbon fuses with helium to make oxygen, the most abundant element on Earth by mass, and the third most abundant in the universe. Oxygen fuses with other nuclei to produce neon, magnesium, and silicon. Massive stars, those more than 8 times the mass of the Sun, push through successive rounds of fusion, each one requiring higher temperatures and each one burning through its fuel faster. Hydrogen fusion lasts millions of years, helium fusion lasts hundreds of thousands of years, carbon fusion runs about 1,000 years, oxygen fusion takes a few years, and silicon fusion, the final stage, lasts about a single day. The star builds up an onion-like structure with concentric shells of progressively heavier elements surrounding the core, hydrogen on the outside, then helium, carbon, neon, oxygen, and silicon. And at the very center sits the final product of silicon fusion, which is iron. Pay attention to iron, because iron is where the story takes a dramatic turn. Iron, 5,6, carries the most tightly bound nucleus in all of nuclear physics, which means that fusing iron does not release energy, but consumes it. Every fusion reaction up to iron has been exothermic, pouring energy outward and holding the star up against the relentless inward crush of gravity. But when the core fills with iron, the energy tap shuts off. For millions of years, the star has been writing checks against its nuclear energy account. And suddenly the account sits empty, with no more energy to support the weight pressing down from above. Gravity does not negotiate. What happens next ranks among the most violent events in the known universe. Without fusion energy to support it, the iron core collapses in on itself in a fraction of a second. Once the core exceeds the Chandrasekhar limit, about 1.4 solar masses as calculated by Subramanian Chandrasekhar, no force can stop the implosion. The inner core compresses to nuclear density as protons and electrons are squeezed together to form neutrons, and then the core rebounds hard. The force of that rebound, combined with an enormous flood of neutrinos from the collapsing core, sends a shock wave tearing through the outer layers of the star. This is a core collapse supernova, a type 2 supernova, and it is briefly brighter than an entire galaxy. Here is the embarrassing secret of modern astrophysics, because we still do not fully understand how this process works. Our computer simulations of core collapse supernovae keep stalling. We model the iron core collapse and launch the shock wave, and in many simulations, the shock wave loses energy and stops before it can blow the star apart. The star refuses to explode. Astrophysicists have been trying to computationally blow up massive stars for decades, and only recently, through enormously complex three-dimensional simulations that account for turbulence, neutrino heating, and magnetic fields, have we started to get explosions that look realistic. The universe clearly knows how to destroy a star this way, but we are still learning. And that matters because it reminds you that science is not a finished product, it is a process with chapters yet to be written. Inside the apocalyptic conditions of a supernova explosion, at temperatures of billions of degrees, and neutron fluxes beyond comprehension, elements heavier than iron are forged. Gold, platinum, and uranium, all the elements that fusion could not build during the normal life of a star, are assembled in seconds through a mechanism called the rapid neutron capture process, or R process. Atomic nuclei absorb neutrons faster than they can radioactively decay, building up to heavier and heavier unstable isotopes that then beta decay into stable heavy elements, which is nuclear physics at its most extreme. But the R process accounts for only about half the elements heavier than iron, and the other half come from something gentler called the slow neutron capture process, or S process, which operates inside aging red giant stars on the asymptotic giant branch. Over thousands of years, these bloated and dying stars gradually build up heavier elements like barium, strontium, and lead by slowly adding neutrons to existing nuclei one at a time. Two completely different astrophysical environments running at two different tempos are together responsible for every heavy element in existence, and astronomers can actually distinguish which elements came from which process by analyzing isotope ratios in ancient metal-poor stars that formed so early they carry the chemical fingerprints of only one or two previous stellar generations. There is also a third factor we only recently confirmed. In August of 2017, the LIGO and Virgo gravitational wave observatories detected event GW170817, the spiraling collision of two neutron stars roughly 130 million light years away. Within hours, telescopes around the world turned to the source and watched a kilonova unfold, a fireball glowing with the spectral signatures of freshly synthesized heavy elements, including lanthanides and actinides. Those observations confirmed what theorists had suspected for decades, that neutron star mergers are prolific factories for the heaviest atoms. The gold in a ring on your finger, the platinum in a catalytic converter, the uranium that powers nuclear reactors, much of it was likely produced not inside a star, but in the violent collision of stellar corpses, thousands or even millions of light years from where our solar system would eventually form. Take a moment to consider the full scope of what I have just described. The universe starts with nothing but energy, then cools and builds protons and neutrons, then cools further and fuses a bit of hydrogen and helium. After that, it waits patiently and silently for hundreds of millions of years while gravity slowly assembles the first stars. Those stars light up, and inside their cores, they forge carbon, oxygen, nitrogen, silicon, and iron. When those massive stars die, they scatter their enriched material across interstellar space, seeding the galaxy with the raw materials for the next generation of stars, for planets, for chemistry, and for life. Astronomers have a word for this progressive enrichment, and they call it metallicity, where in astronomy the word metal means anything heavier than helium, which means the sun by astronomical standards qualifies as metal-rich. The first stars carried zero metallicity, and we exist because that number increased generation after generation. Our sun is not a first-generation star and could not be. It contains iron, nickel, oxygen, and silicon, elements that could only have been produced by stars that lived and died before it was born. At minimum, our sun is a third-generation star, built from the recycled remains of its stellar ancestors. And so is the Earth, and so is every living thing on it. You are made of star stuff, but more precisely, you are made of dead star stuff, recycled and secondhand, with the atoms in your body serving as cosmic hand-me-downs worn by at least two previous generations of stars before they ever found their way into you. The iron in your blood, the calcium in your bones, the oxygen filling your lungs every time you take a breath, all of it was manufactured inside a star that exploded before the sun existed. Nitrogen in your DNA and the phosphorus in your cell membranes were forged in supernovae, and that is not poetry or metaphor, but scientifically verifiable truth. We figured it out using spectroscopy, which splits starlight into its component wavelengths so we can read the absorption lines like a barcode. Every element leaves its own unique signature in light. And by reading those signatures, we decoded the composition of stars billions of light years away without ever visiting them. We build gravitational wave detectors sensitive enough to measure a distortion in space smaller than 1/10,000th the width of a proton. We pointed the most powerful space telescope ever built at the edge of the observable universe and watched the first stars flicker into existence. Evolved primates on a tiny rocky planet orbiting an average star in the outer suburbs of an ordinary spiral galaxy traced the genealogy of every atom in existence, and that is what the human mind is capable of when it refuses to accept that something is just the way it is. The periodic table is not a classroom poster. It is a cosmic achievement, billions of years in the making, written in the language of nuclear physics, edited by supernovae, and distributed across the galaxy by gravity and violence and time. Its most astonishing entry is not uranium or gold or any exotic heavy element. It is you, an arrangement of atoms complex enough to contemplate its own origin. Consider this. The universe is not done. Right now, somewhere in this galaxy, a massive star is approaching its iron moment. Somewhere else, two neutron stars are spiraling toward collision. New atoms are being forged at this very second that did not exist yesterday, because the periodic table is not a finished document, it is a draft, and the universe is still writing it. That is what this whole story really comes down to, not just matter assembling itself, but matter becoming aware of itself and realizing the story is still being told.